what do you think could be some uses of the line spectra? And of course there's some right or wrong answers here. You're not going to be marked right or wrong. But discuss with a neighbor if you need to. What are some ways you think we could use the line spectra? Put in something. And we'll count down here. We'll count down 5, 4, 3, 2, 1. Okay, there we go. To identify possible elements in different stars or planets. That's a good one. Another one here is to identify atoms. That's good. Element fingerprint. Right here. Fireworks is another one. And most of the rest of these are sort of in the ballpark. Okay. These are ones that I'd like for you to know, and some of them did show up on the Socrative app here. One of those is in element identification. So like we said, some said there, that's like whatever's in the stars or planets. Another one would be what we call neon lights. Now, of course, in the real world, neon lights only have one color. And that color that we saw was, yeah, kind of orangish or reddish color. Okay? Anything else that you saw that was any other color and they were called neon lights, guess what? You've been lied to your entire life. They are not neon. There are some other elements that are in there. So different elements produce different lights. And of course today we've gotten away from neon lights. Most of the lights that we see where they're brightly illuminated like that aren't filled with gases filled tubes anymore. They are LED, the stuff that we're going to be putting in here. We're going to be putting in college-wide LED lighting. And so LED lighting is what's used typically in things that we often associate with neon now. But it used to be that if we wanted different colors, we'd have to fill them with different gases. Somebody mentioned 4th of July, we see fireworks. And so just like we saw different colors here with the flames, we get different colored fireworks by putting in different elements.
Fires. So you're telling like ghost stories or have a friend tell ghost stories and then like you sneak up and throw the power on the flame.
Yes. I don't know what solids are you using.
I think I'm actually just going to get like powderized copper.
Okay. Yeah, copper will do that, the powdered.
Green flames.
Yep. Yep. And if you have lithium, never mind, I won't mention that. I don't want to give you any ideas or get any of you hurt. Okay? And then another one here that was not mentioned is that the universe is expanding. The universe is expanding. And for this one, I actually have a website that helps show us this concept, and I will link it to the D2L content section for today. But on this website, this here shows us what happens when we look at the stars. Now it's kind of interesting here. The element helium, in fact, most of these noble gases were some of the last elements to be discovered. Anybody know why it was difficult to discover or learn of these elements?
The noble gases?
They're noble gases, which means they are generally non-reactive. And so the original elements were discovered based on how they reacted with each other. And since they didn't react with anything, we didn't know about them. And the first of the noble gases to be discovered was argon. And that's because air, the fifth most abundant gas in air, is argon. But the second noble gas that was discovered is this element, helium, and that was discovered in the sun. Anybody know the Greek sun god? Helios. It's Helios. Helios is the Greek sun god, and this element was named helium because the first place helium was discovered is in the sun. And that's because the composition of the sun, it really isn't too interesting. It's made up of two elements. They are hydrogen and helium, and that's it. It turns out if we looked at all the other stars in the universe, we see that they're made up of two elements. They are hydrogen and helium. And there's some other elements that might be in there, but those are by and far, way far, the two most abundant elements. And so when we look at the composition of stars, their spectrum is very set. Every star is going to have pretty much the same spectrum in there. We know exactly what to look for. These same things, if we came back next week, or we came back 2 years from now, or 15 years from now, we'd see the exact same lines every time that we come back there. Just like the stars are always going to have the exact same lines. But what we notice is this, is if we look at stars, and now you see there's two ways I could select here. I could select to have a star move towards the Earth. If I had the star move towards the Earth, I'm going to use the speedometer. I'm going to increase the speed. Notice where this line, these lines are shifting. Notice that they are shifting in this direction here. If they're shifting in this direction, that's called a blue shift, because they're shifting more to this blue side. Turns out, though, when we look at stars, we don't see that. We do not see them blue shifting. Rather, when we look at distant stars, what we see is this. Notice now as I'm increasing the speed, now we are going away from the Earth, and this is a speedometer right here. As we increase that speed, these lines are shifting more to the right, and we call that a red shift. And so when you look at distant stars, we don't see them blue shifting, we see them red shifting. And it turns out that the further away the stars are, the faster they're moving away from the Earth. So when you hear scientists talk about the Big Bang as being how the universe originated, this is in part where that idea comes from, is that when we look at distant stars, those distant stars are moving further away from us, faster away from us, than those that are closer to us. Now, this whole concept is based on something called the Doppler Effect. This is based on something called the Doppler Effect. And if we were to look at the Doppler Effect, and let's see here if I have a diagram. I don't have one. So what I'm going to do is I'm going to draw a diagram here. I'm not much of an artist, but we'll at least make this be a happy person because spring break is coming. Okay, so let's say that we had a person standing here and we had a car, and that car, again I'm not an artist, is going to lay on the horn. And right now if the car is sitting there, we might perceive the sound waves looking something like this, where the distance between these two waves right here is referred to as the wavelength. But now we're going to put a car into motion. And this is where I have a second video here to describe the Doppler effect.
Okay, welcome to the Adler Scientific Society. We're going to make a little video today about the Doppler effect. We're here outside because most people have heard the Doppler effect. They might not know it, but we've all experienced it. So let me show you what I mean.
Okay, so you heard there as the vehicle went by, how the pitch dropped.
So the funny thing is that when you're in the car, it doesn't sound the same. So we got to listen to that right now, try and figure out what's going on. Here we go.
Okay, so then you heard that when they drove by and sat in the car, how that pitch remained the same all the way across. Now, the reason why, the first one, why we heard a difference is because that car was in motion and was moving away from the stationary observer. And if it's moving away from the stationary observer, we want to explain why we observed what we did. And this is where you get to come up with your explanation. We have an object that's moving away from a stationary observer. What do you think happens to their perceived wavelength? In other words, this person is sitting still, this car is going in motion away. What happens to the wavelength? Does that wavelength get longer? Does it get shorter, or does it stay the same? Okay, let's get our answers locked in. We'll count down. 5, 4, 3, 2, 1. Definitely longer. And that's simply because if it goes in this direction, what is it? Think of it as a spring. What's happening to that spring? It's getting stretched out. Now those wavelengths get longer. As a result, then, we hear what we did in that video, that pitch winds up dropping down. Same thing if you listen to, say, NASCAR on TV. You watch it, you hear the cars go by, you hear meow, meow, meow as they go by. That has to do with the Doppler effect as that car moves away from that microphone. Now we could replace this car with a star, like we were talking about before, and it's the same thing how we talked about these being red shifted, because it turns out that these wavelengths here are associated with longer wavelengths. When they red shift, they're longer, which means those wavelengths are being stretched out. So scientists know then that we're dealing with an expanding universe because the fact that the distant stars have that red shifting that we observe.